Okay, next speaker is Professor Yury Nikulin from the University of Turku in Finland. Thank you very much.
Thank you, Juan. And good morning, everyone. So, welcome to my presentation. So, first of all, I would like to say a few words of gratitude to the organizers for giving the opportunity to present today here and for organizing such a nice event. So, yesterday we were discussing a lot about the importance of such events to keep communicating in presence with people, because it gives us a source of exchanging ideas, and new ideas may come out from such cooperation. And today my talk is actually an example of such situation. So now I will use time machine, which is called human memory, and most of you probably were present 2 years ago at another nice event which was organized in Alicante. So Marco was the main organizer of that event. It was a conference in honor of Professor Boris, who know him, so in honor of his 75 birthday. Yeah. And at that, I was pleased to give a talk at that event. And after that, we had a nice, relaxing walk to a dinner place. So my talk was about KKK conditions for index for fuzzy optimization with index functions. And we were discussing a little bit about the concept of convexity. And I was in a group of 3 people, so Boris, me, and Juan Enrique. Juan Enrique pointed out that he has one paper published earlier about characterization of index functions for differentiable case, which at that time I was not aware of, and we were start thinking about could be some kind of similar results, somewhat transferred or generalized to Nonsmooth analysis settings. So, and this is how actually the topic which I'm currently working on was originated. So, of course, in a Nonsmooth case, when we are trying to generalize to Nonsmooth case, well, we are using some nice subdifferentials. So I'm coming from an optimization group which somewhat favors as a methodological tool, favors Clarke subdifferential. So, but of course, many other more refined and more tuned subdifferentials exist. So, and in today's talk, I will try to make a comparison of Clarke versus limiting subdifferentials, which was proposed by, as you know, classical concept of Boris in his book, yeah, in his main multiple books. Yeah. Then basically the main research question was, can we generalize one theorem which relates to the characterization of functions which are indexed to the same heter from differentiable case to non-differentiable case by kind of looking at corresponding replacement of gradient with Clarke and multiple subdifferentials. So basically, I can already kind of pre-announce the answer that in Clarke case we do have some problems with such generalizations, but in a limiting subdifferential case, everything looks nicer, much nicer. Probably not very surprising results for you, because you all know that Clarke subdifferential is due to convexification may include lots of directions, lots of subdivisions, which are not very informative, let's say, like this. So, but anyway, this would be a kind of one more confirmation of the fact in some sense. Yeah. The structure of my talk will be like this. So hopefully I will have enough time at least to present part of it. So we start with the original theorem, and then very quickly through some Nonsmooth preliminaries, basic definitions of concept of complexity. So in a single objective case, it's very much related to the concept of stationarity and implication about global minimality. And then we will see the case that in the Clarke case, we have a counterexample which shows that straightforward generalization of the theorem will not work. So, and then same example cannot be considered as a counterexample in the which case. So, as a disclaimer, I would like to say that these results are not finished yet, so they are like a work in progress. It's more like, say, still a bunch of working ideas. Some part of these ideas already published, and it will appear in the first issue of Journal of Polish Academy of Science on Role and Cybernetics this year. So, but some of the results are still in discussion, and I hope to finalize them personally in discussions with Boris if I have a chance to visit him maybe at the end of this year or beginning of next year. So let's move on. This is the original paper of Juan Enrique, published in 2009, which concerns characterization of a finite family of differentiable functions, which are basically index with respect to same mapping at that. Yeah. So basically, when we are saying that a collection of functions has common indexity property or condition, so it implies basically this, that the gap on the left side is basically bounded from below by the left-hand side scalar product of the gradient and vector valued mapping atom. So basically, we have a finite system of equations. For each function, we have this type of an equation. So eta is the same for all equations. And so basically, the smooth version of the theorem is according to Enrique paper. So we have equivalence between several statements. So the first is we have a finite number of index functions which are respective to the same eta. So, and if we consider a scalarized function where scalarization is taking with non-zero, actually non-negative multipliers. So then this function is also indexed with respect to the same mapping eta. Yeah, and then so obviously functions are index, scalarized function is indexed, and also the most important statement in this theorem probably that the characterization itself, that for every non-negative lambda, every stationary point of the scalarized function is a global minimizer. Yeah. So basically, the proof is not very complicated. So basically, it is based on application of Gale's alternative lemma, which helps us to separate a system of linear equations in these cases. Yeah? So Well, as I said, so the idea is to transfer, to see if direct transfer of these results to Nonsmooth case is available. And as I said, so we are going to use a comparison or beta of two subdifferentials. So Mordovich limiting subdifferentials, which is a traditional definition of these as basically limit superior at sequence of points converging to x of the free share lower subdifferential. So, and second choice, second agent is a Clarke generalized directional Clarke subdifferential, which is defined with first we define the Clarke generalized directional derivative, and then so with the help of this derivative we define this subdifferential itself. So here it's important to say that limiting subdifferential is defined for a larger class of functions, basically for lower semi-continuous functions, whenever Clarke subdifferential is usually defined for a locally which is continuous function. Therefore, to make this kind of comparison more, say, fair play, so we should limit our focus to ABC functions only. So yeah, and of course, as we know from general theory of those two subdifferentials, well, Clarke is always convex. Yeah. So Mordovich subdifferential records limiting subgradients without that convexification, so it is a little bit finer tuning, and compare also to Fisher subdifferential, which may not exist, or which differential will always exist in our case. Yeah. So then, of course, for convex functions, all these subdifferentials coincide with the convex subdifferentials, and so we are interested in analyzing extension, not extension, but say alternative concept to convexity, which is convexity. Yeah. So, and of course, all these kind of theoretical properties of subdifferentials, they are very critical from technical point of view. They are critical for the proving theoretical results found about convexity. Yeah. Yeah, convexity basically in Nonsmooth case, well, we just require that convexity condition, existence of theta functions, and convexity condition should hold for the corresponding subgradients taken from subdifferential, relevant subdifferential, either Clarke or Mordovich. Yeah. So general definitions, and then for the finite family, so we basically have the finite family of vector functions at convexity. Well, complete analog of differentiability. Just here we just take subgradients. Yeah. So basically, in a classical case, for one single valued function, so if a function is differentiable, and index we have that every stationary point is a global minimum. This is a very fundamental property in differentiable case. And let's see if this kind of property preserved in Nonsmooth case. Well, in Clarke case, we need to have everything technically correct. We need to assume the closeness of a specific cone. This is called, I think it's Clarke generated cone. So the cloneness of this cone is required to eliminate some pathological cases, which are not really very descriptive cases. Yeah. So just a technical, more or less technical assumption about cloneness of that cone will guarantee that criteria for inversity is that every stationary point, stationary of course in Nonsmooth case, implying that zero belongs to the corresponding Clarke subdifferential. So it's a global medium. The point is a global medium. Yeah. So in orthogonal case, whenever we narrow our focus to only locally fixed functions, so then convexity with respect to theta, basically we do have the same kind of property that zero and zero when we have stationarity, then zero belongs to the differential. So then we have a global minimizer. So this is quite well-known fact. So I will skip this proof, which is quite simple. Yeah. So then basically in the differentiable case on the Britten theorem, the main kind of footprint or technical difficulty in the most essential part of the proof is to when we prove equivalence of four statements. So 1 implies 2, 2 implies 3, 3 implies 4. It is quite easy to prove. So what is less easy to prove is actually that from 4, from that statement, the last statement about a scalarized function, you know that the first statement of the theorem. This is the most difficult part, and this is where actually we found a problem with the generalization to the Clarke case. So basically, we have an example. So some function looks like this. Yeah, so it's for negative part, it is just a linear function. So, but for positive, it's a little trickier function, but not too much trickier in the Nonsmooth case. Yeah, so that we can compute those subdifferentials, and they are kind of handy to deal with. Yeah. So as we can see in a Clarke case for the first function, at point 0, subdifferential is interval from 3 to 7. So whenever for the second function, which is absolute value 3 times, it's just a symmetric interval minus 3. Yeah. So then if we take this point, base point at 0, so we can calculate the value of function f2 at 0, so and check inversity condition for different directions. So we can take two extreme symmetric directions, 3 and -3, to see what kind of conditions we have on our mapping on our theta function at base point 0. So here, from f2 function analysis, the mapping should belong to symmetric interval from -x to x. So, and then basically, if we consider first function r1, so and applying the same mechanism for considering different directions. Yeah. So now our interval, our subdifferential at 0 is not symmetric, and it doesn't include 0 itself. so this interval 3, 7, so which leads to basically two constraints which are contradicts to each other, which means that there is no possibility to find such function eta. Yeah. So we have a counterexample which tells us that Clarke case is not easy to analyze, to generalize, but actually we do have proven a theorem which looks similar to differentiable case with a slight modification of the last statement, and this modification will do a trick. So we also can formulate analytical theorem, but not a straightforward analytical theorem. So some modifications are needed. So whenever when we consider Mordkovich subdifferential, and if we analyze the same function, which was a counterexample function in Clarke case, so in Mordkovich case, because now subdifferential at point 0 for the first function is not anymore 3, 7, it is 6, 7, is more kind of refined. Yeah, so some directions which were present at the Clarke case, they are missing in Mordkovich case, and this means that those constraints which we impose on eta functions, they are not contradictory anymore. So everything is seems to be working fine with this example. Yeah. So yeah. Also, the condition 4 in this example so can be shown that it is fulfilled. So, and also in if we check condition 1 in this example, then also yeah, we have some interval for the eta function. So, but everything seems to be working nicely. So we just only need to assume that our function is allowed to be piecewise function, piecewise linear in this case. Basically, a general definition of complexity doesn't really contain any kind of limitation on the type of function what would it be. So, and it seems like this example cannot be used as a counterexample in the Mordkovich case. So, and then we basically, it seems like since we were not able to find a counterexample, there is a hope that we can prove the theorem. Yeah, we can prove the theorem. Finding no counterexample is necessary, but not a condition for yeah. They still need a proof of actual proof of theorem. Yeah, so the theorem will now looks like well, it's just a shortened version of the theorem. Instead of all the 4 conditions, just is jump from condition 4 to condition 1 is present here, because this is the main culprit of the entire theorem. There's this, so basically going more or less automatically. Yeah. So once again, so we have a scalarized function. So, and for all non-negative scalarizing multipliers, every stationary point of that function so is a global minimizer, and we want to prove that this implies that there exists a function eta such that finite family of function is an index with respect to same eta. Yeah, first kind of step, we should look at our functions individually. So we just set those multipliers 0 except just 1. So and then the condition implies that every stationary point is a global minimizer of the individual function. Yeah, it's just like a trivial case. So then, well, of course, for local Lipschitz functions, we basically even can specify how the function eta may look like. So it's quite standard formation in Nonsmooth analysis for such functions. Yep, so when you take a gap divided by norm square. So, and this is as very small technical validation shows that this choice of the function works in our case. Yeah, so what is a bit more kind of less obvious is basically to prove existence of common eta. So we can probably do the proof by arguing by contradiction, assuming that no such mapping works for all the functions, that there should exist at least one function where condition, investigating condition fails. So we need to construct a scalarized function, and then we need to take a subgradient which is of one function, which is a linear combination of the subgradients of the other functions. In that way, we can, first of all, we can guarantee stationarity for the scalarized function that zero belongs to subdifferential, limiting subdifferential of the scalarized function, and then basically from this and from this connection between one subgradient and the linear combination of the others, we can guarantee that basically we have here 0 on the right hand side, so which implies that we do have so we do not have global minimizer. So that's this kind of I don't present here all the technical details, just maybe milestone ideas of that proof that we have to consider. Yeah. So this is actually how we are kind of researching in this area, as I said. So there are many more results which we obtained in parallel for Clarke case, as I said. So we have proven also analog theorem by a little bit modifying the last condition, and this is already kind of piece of work which is done and which will be published very soon. Like if you are interested, you will learn about the certification for that. So the rest of the work is still work in progress. So we are still discussing some ideas and how to strengthen results and maybe get something more interesting out of this theory. So, but the main kind of message what we have here, as I already kind of said it previously. So, of course, we considered only two cases, the two subdifferentials. Those of you familiar or prefer the results of differentials, we start thinking about other cases. This might be also interesting discussion for us. But we were concentrating on those two. So for us, Clarke and monopolistic differentials are most interesting type of differentials. Yeah, but of course you can consider other cases. Yeah, so yeah, we do have a very nice theorem. So and Juan is not here today, but please pass my thanks for this. Yeah, yeah, for this fruitful discussion, which generated a stream of thoughts. I would say, yeah, and still we are working on that. Yeah. So yeah, Clarke case, due to the more general structure of the Clarke differential, appears to be tricky, and straightforward generalization is not possible. So, but Boris differential wins in this battle, wins in some sense, yeah. So that it shows, we can somehow say that it shows a little bit better, more close to what happening in a differentiable case, or the Polish differential has the same meaning in a Nonsmooth analysis in this situation as gradient. So what Clarke fails here. Well, maybe not as surprising. I'm not saying that this is kind of ground-shaking news for you. Many of you get used to see this kind of situation in Nonsmooth analysis, but this is just one more interesting confirmation and interesting comparison for us. It was interesting to see and analyze what's going on. Yeah, so there are some classical references, of course, the original paper from Enrique, and some classical books which relates to corresponding subdifferentials and the concept of convexity, according to Raymond, which was the first one who actually generalized the convexity definition to Nonsmooth case. Yeah, thank you very much once again for listening, for your time. So maybe we'll be ready to answer your questions if any. Yeah, thank you.